We're doing it live, children. Okay, so in this problem, this is a work energy problem, or rather a work power problem for this. It's practice problem C1 from the work energy unit. And in this, we have Gabe the gardener. Gabe is pushing a 485 Newton lawnmower with a force of 215 Newtons. We know the handle of the lawnmower makes a 145-degree angle with the mower. Gabe's got to cut 36 lengths of the lawn, so that's 36 back and forths, each of which is 75 meters in length, so nearly a football field. He finishes this job in 54 minutes. We're looking for three things here. How much work does Gabe do over each length, so just one? How much total work does he do? And then how much power is that? So let's just start off in part A here. We're looking for work over one length. And we know that work, W, is F dot delta X. And some people put delta X, some people just put an X here, some people actually put a D for displacement. The key is recognizing is that is a displacement there, whatever it is you're using, and it's a vector. And it's important that this is a vector because when we say F dot delta X, we're not just multiplying. We are taking the dot product, which really means that this is Fx cosine of some angle. We need some angle theta here, the angle between the force vector and the displacement vector, to give us our proper value of the work. Now, if we go to put in some values here into this equation, we need to be a little careful because we're actually given 2 Newton setups in this problem. We're given the 485 Newtons and the 215 Newtons. Well, this 485, that's the weight of the lawnmower. Weight doesn't pop up anywhere in these equations. This is a work, remember, not a weight. So this 485, this is a red herring. It doesn't do anything in this problem. What we want is the force Gabe is pushing with, the 215 Newtons. So we can say that force, 215 Newtons, multiplied by a displacement, which is 75 meters for one lawn. And look, right there, we just got Newton meters, which are joules. That's our energy unit. Multiplied by the cosine of some angle. Now what we're going to do here is we're going to pause this video for a second. I want you to try to figure out what the angle we should put in to this cosine term should be. I'll give you a hint right now. It's not 145. When you unpause it, we'll see what it is. So let's take a look at what this angle could actually be. First, that angle has to be between 0 and 180 degrees. It'll never be greater than that. Because if your forces and your displacements, so we'll call this a displacement and this the force, that's 180 degrees right there. If that's your force instead, you wouldn't go around like this. You would go through the smallest angle possible. So your angle is always going to be 0 to 180. Now in this problem, in every problem, I always like to redraw my forces. And you want to draw these forces from the same starting point. We're not adding forces with the head-tail method here. We're trying to see what component of a force maps onto the displacement. So here is our force vector, F, and our displacement vector is going to the right. There's our delta X. This angle here is what we actually want. Because if I broke my force vector up, I could see that a component of it, this is the Fx term, that's the F cosine theta, is sitting on that displacement, the red X vector there. So that's actually what I want. So this blue angle is what I want here. To get it though, if I backtrack the actual force line, I know that this angle is 145 degrees, and since going from here to here supplementary is 180, we can say that our blue angle here is just 180 minus the 145, which does indeed give us 35 degrees for our angle. We also know that has to be 35 degrees, or rather it has to be at least less than 90, because Gabe is the one pushing this cart forward. He's helping the motion of the cart. that means there's a positive work being done here. That means that cosine has to be less than 90 to remain positive. If that angle was 145 degrees, that cosine term, cosine 145, would be negative, and that would imply that Gabe is pushing backwards against the motion of the lawnmower, which that doesn't make any sense, for one, and two, that's very dangerous. Like, that's how you get your foot chopped off. So don't do that, okay? So we know in a number of ways that this work must be cosine 35 here. So running numbers here. Where's that calculator from my own years ago of physics? We get 215 times 75 times the cosine of 35 degrees. Make sure you're in degrees. If you're not, you're going to have a bad time. And we find that the work for part A is 13,200, and if we just round up, we'll get 9 Newton meters or joules. If we want to find for part B, what's the total work done? Well, Gabe did this 36 times. He did this every single lawn he walked through. So we just have to take this number, 36,209, and multiply it by the 36. So our total work here is just the work of one lawn multiplied by 36 lawns. We get a giant number here, 475,524 joules, because it's still a unit of work. And for our last part here, part C, we want to look at what's the average power output that Gabe is exerting. And we know that power, capital P, is just a work divided by some amount of time. Well, we know in this case, the work Gabe has done, 475,524 joules. And what's the time that Gabe went through? Well, Gabe did this in 54 minutes. That's not cool. We don't want to put minutes into our denominator. We want that to be in SI units of seconds. So we need to say that 54 minutes, we got to get that to seconds. And we know there's 60 seconds in 1 minute. Our minutes go away here as we train track that, or fence posted, or dimensional analysis, whatever you want to call it. We get 3,240 seconds, which now when we divide this, 475,524 divided by 3,240, we get a value of 146.77 watts, or joules per second of power. So that's what's going on in a problem like this. We see here that there's really nothing crazy going on, but we need to be careful that we're not using weights. We're using forces applied to the object, because it is something you do, work is done. We need to make sure that we're very careful with our angles in this problem. It's very helpful to redraw your forces, have them start at the same location, and then find the smallest angle between them. And then once we do that, we can find work, we can find total works for each time they do that, and then with that idea, we can find power as well. So this problem is finished. Until next time, adios, and take it easy.